So there are multiple ways you can make this absorber. So a very simple way would be to essentially use something like an anti-reflective coating, right? So anti-reflective coating, it helps you maximize absorption at one particular wavelength, right? So you could use something like a silicon nitride, which maximize it for a solar spectrum. But again, it wouldn't make you, it would give you some kind of a good absorber, but not the best absorber. So again, the way to make a good absorber across a range of wavelengths and make it a better step function is to use layers of different material. So most of these, at least ideal absorbers, what they try to do is use different layers of different dielectrics, different metals, to try to make that optical spectrum more like a step function. So this is one way to do it. Another way to do it, which is actually used most commonly, is this material called cermat. It's essentially a material which is combination of both ceramic and metal, and it's essentially has these ceramic and metals mixed into each other, and overall it gives you absorption spectrum which is more reflective of having these multiple layers. And then you could use texturing and all the things we talked about when we discussed light trapping. So it's very similar to that, the techniques. But the idea here is to produce the step function in terms of absorption coefficient. And it needs to have some other properties as well. So this heat collecting element, it needs to, so I can design these things with all kind of materials, but they won't be thermally stable up to high temperature. So I need to make sure that this material is thermally stable. It's resistant to shock because when these things expand and contract as the fluid heats up and cools down. So this is what is most commonly used. This is a cermat absorber. This cermat is ceramic plus metal. So it has essentially combination of both the ceramic material and these metal particles. And if you look at it in terms of spec, it has a pretty decent ideality factor. So it has a absorption of almost 96% in the solar spectrum range, and has an emissivity of 10% at 720 Kelvin. So if you multiply those two, it gives you a ideality factor of around 85-86%. And this is how people who work in the lab and they want really good step function in terms of their absorption coefficient. So what they do is again use different layer of these metals and dielectrics and stack them on top of each other. Just like when we talked about anti-reflective coating, you did that set problem on it. So the more the layer of materials you use and more the number of films you use, more ability you have to tune your absorption, to tune your spectral function. So this shows here for increasing number of layers. So if you have just one layer versus if you have 5 layers versus if you have 11 layers, you can make this closer to being a step function. Right? So keep this in mind. Shortly I'll talk to you about thermophotovoltaics, and it uses the same idea. You want this absorption to be a step function, or this emissivity to be a step function. Now the other part of it was this storage system, and again it depends upon how much delay you want between your sun going down and your and the ability of your power plant to continue powering beyond. Excuse me. You're having a class. Do you think if you can move?
Oh, no, this is the grand opening of our showcase. It's very important.
Just one moment. We'll leave just in 2 seconds.
So if you're using this plant to essentially power, if this plant is located in Vegas, so did any of you go over the long weekend? So if you went to Vegas, right, you have your sun which goes down in 8, and you want this power plant to power the strip over the night, right? So you wanted to have enough storage, like 3, 4, at least 5, 6 hours of storage. So the way you develop this storage is, again, you pump this fluid from the cold tank, and it heats up during the course of the day, and you store it in the hot tank. And when the sun goes down, you take this fluid from the hot tank, use it to power this steam generation power plant, and then use it over the course of the night. So the bigger tanks you have, the more efficient tanks you have, the more capacity you have in terms of storing your energy. Now, these tanks are typically this fluid which is used for this heat transfer. It's the first systems which were built used to use steam, and I talked about if you are placing this plant in a place which is very high direct normal incidence, which is typically a desert, the thing you least expect to find is a good water resource over there. So it's foolish to use steam. So the options you have are typically oils. These synthetic oils have good thermal capacity, but again they have high vapor pressure as well. So when you fill gasoline in your car, right, you notice the smell, and that's because the high vapor pressure of these systems. The critical point of these systems are much lower. So it's expensive to design these systems. They tend to the storage tends to become expensive. So the more common choice, which is nowadays becoming more popular, is to essentially use synthetic oil. To use molten salt. The problem with molten salt is that it freezes if you go below 180 C. So if you essentially are going to build a plant with the 180 C and with this molten salt, and during the night it will go below 180 C. So you need to make sure that you pump this fluid out of at least the pipes which are running, so they don't the fluid doesn't get frozen over there. And again, the big challenge over there is to essentially either manage the temperature always above 180 C, so it never freezes, or to pump it out when you pump it out of the system when it's starting to become cold. So this is how your storage of this would work, right? So this would, the blue curve over here is your sunlight, your direct normal incidence. So it will start at 6 a.m. in the morning, and it maybe goes up, if it's a warm summer day, it goes up till 7 or 8 in the night, right? And if you want your energy conversion to essentially, happen at a delay of 3-4 hours, you essentially take this direct sunlight, and this light blue curve is what is feeding into the tank. So this is energy which is going into the tank, and then when your tank saturated in terms of capacity, or you essentially want to start producing electricity, you take the energy back from the tank and use it to power the steam. So typically most of these systems, they at max have a capacity of 4 to 5 hours storage. So it's not enough to power the strip throughout the night yet. But if you design, you need much bigger tanks for that. But right now they have, if you're using a steam-based storage, it's around 1 hour. If you're using oil-based storage, it's typically 2 hours. If you're using the soil-based storage, it's 4 to 5 hours. Okay, so this is a picture of one of these tanks. So these are some of the bigger solar thermal power plants. This one is called Andasol. It's based in Spain. And even from when you zoom in on the satellite picture from Google Maps or Google Earth, you'll be able to locate these two tanks situated in the middle of the plant. And these ones are using this molten salt fluid. Okay. So that's all I had to talk about solar thermal. I've uploaded a few more handouts on the class website if you want to read about it more.